This question refers to the elements in the first three periods, hydrogen to argon, of the periodic table. Part A. Select an element from the first three periods that fits each of the following descriptions. 1. The element that forms a 1- ion with the same electronic configuration as helium. Having a 1- ion means that it has gained an electron, and so we need to take a step back from helium on the periodic table. Taking a step back from helium on the periodic table would give us hydrogen. So the answer to part 1 is hydrogen, which would give us the mark for part 1. Part 2. The element with the highest first ionization energy. First ionization energy increases diagonally from the bottom left to the top right of the periodic table. Therefore, the element with the highest first ionization energy would be in the top right of the periodic table, and that element is helium. So to get the mark for part 2, you need to write helium. Part 3. The element in period 3 which has the successive ionization energies shown below. What we first need to identify is the large jump in ionization energy, and that jump is from second to third, which means that it has a 2+ charge. So we're looking for an element with a 2+ charge in period 3, and this element is magnesium. So to get the mark for part 3, we need to write magnesium on the answer line. Part 4. The element which forms a compound with fluorine that has octahedral molecules. What this question means is that we're looking for an element that will form 6 bonds with fluorine. In other words, produce a compound with hexafluorine. And the element that will do this is sulfur. So to get the mark for this question, you need to write sulfur on the answer line. Part 5. An element which reacts with water to form an acidic solution. An example of this would be chlorine, and the solution that chlorine would form would be a mixture of hydrochloric acid, so HCl, and hypochlorous acid, which is HOCl. Both are acids, so would be an acidic solution, and therefore to get the mark for part 5, you write chlorine on the answer line. Alternatively, fluorine would be an acceptable answer to part 5 and would form hydrogen fluoride and hypofluorous acid. Part 6. The element X which forms a compound with hydrogen XH3 with a molar mass of 32 grams per mole. What this question is saying is that the relative formula mass of the compound XH3 is 34. So to work out the relative formula mass of X, we would do 34 minus 3, because that's the relative formula mass of H3, and that gives us 31, and the element with the relative formula mass of 31 is phosphorus. So to get the mark for part 6, we write phosphorus on the answer line. Part 7. An element which forms a compound with hydrogen in which the element has an oxidation number of -4. So what we're looking for is a compound of XH4, so a compound or an element that can bond 4 times with hydrogen and have a negative oxidation number of -4. So that means we're going to look at group 4 on the periodic table. And the element that will do this is carbon. So to get the mark for part 7, we need to write carbon on the answer line. Part 8. The element which has a density of 1.33 times 10 to the negative 3 grams per centimetre cubed at room temperature and pressure. So the volume of any gas at room temperature and pressure is 24,000 centimetres cubed. So what we can do is take 1.33 times 10 to the negative 3 and multiply this by 24,000. This will give us the relative formula mass of the element, and it equals 32. So that means that the element we're looking for in part 8 is oxygen. So to get the mark for part 8, we write O2 on the answer line, because each relative formula mass of oxygen is 16, so O2 would be 16 times 2, which equals 32. Part B. Table 1.1 shows some properties of period 3 chlorides. Explain the properties shown in Table 1.1 in terms of bonding and structure. Firstly, we're going to talk about the properties of NaCl and MgCl2. The first thing we need to comment on is the type of bonding. These are giant ionic lattices. Then we're going to talk about the electrical conductivity, and notice that it goes from poor to good when it goes from solid to liquid. And that is because the ions are mobile in liquid states and not in solid states. So they can carry an electrical charge in liquid states but not solid. And that is why they are better electrical conductors when they are liquid. So now we're going to talk about SiCl4 and PCl3 and SCl2. All of these are simple molecular structures, and so they are held together by London forces of attraction. And therefore, we need to make an overall comment on the melting points. So NaCl and MgCl2. And because ionic bonds are stronger than London forces, that is going to impact the melting points of these two different types of compound. And it means that NaCl and MgCl2 have higher melting points because they're held together by ionic bonds and not London forces, or not only London forces. To get the 5 marks for this question, you get 2 marks for talking about the bonding and structure of NaCl and MgCl2, so saying that they are giant ionic lattices and that the ions are mobile in liquid state gets you 2 marks. You then get another 2 marks for talking about the bonding and structure of SiCl4, PCl3 and SCl2, so saying that they are simple molecular and that they're held together by London forces gets you 2 marks, and your final mark comes from saying that ionic bonds are stronger than London forces. This question looks at reactions of hydrogen peroxide and of cobalt-2 ions. Part A. Aqueous hydrogen peroxide decomposes as shown in equation 2.1. The reaction is catalyzed by manganese 4 oxide, MnO2. A student investigates the decomposition of a hydrogen peroxide solution as outlined below. 1. The student adds 50 centimeters cubed of H2O2 aqueous to a conical flask. 2. The student adds a small spatula measure of MnO2 and quickly connects the flask to a gas syringe. 3. The student measures the volume of oxygen every 200 seconds. Part 1. Process the results as outlined below. 1. On page 5, plot a graph of volume of O2 against time. Use your graph to find the rate of the reaction in centimeters cubed per second at t 500 seconds. Show you're working on the graph and in the space below. So firstly, what I've done is I've written a scale for time and the volume of O2. Next, we need to plot the results. So 0, 0 is our first point, and here we mark it with an X. Then we have 215, again marking with an X, 428, and then 636, 841, 1046, 1200 and then 48, and 1400 and then 50. So here I have plotted all of the points that we have been given in the results table. Next, we need to draw a curve of best fit. So a curve would be connecting all of the points because they form a curve rather than a line of best fit. The next part of the question, we're asked to find the rate of reaction in centimeters cubed per second at t 500 seconds, which means we need a tangent at t equals 500 seconds. So drawing a tangent at t equals 500 seconds using a ruler, we draw a straight line at t equals 500 seconds, like so. Then, to work out the rate of reaction, we need to work out the gradient of the tangent. So working out the tangent, if we take point 40 on the tangent and follow it down to the x-axis, we get 700. And then taking point 20 on the tangent, following this down, we get 0.180. So working out the tangent is the change in y over the change in x. So that would be 40 minus 20 divided by 700 minus 180, which gives us a rate of reaction of 0.038 centimeters cubed per second at t equals 500 seconds, writing this on the answer line. To get the 5 marks for this question, you get a mark for correctly labelling the graph and having a sensible scale. You get a mark for plotting the points correctly, a mark for drawing a curve of best fit, a mark for plotting the correct tangent at t equals 500 seconds, and a mark for the correct calculation of the gradient of the tangent, 0.038 centimeters cubed per second. Part 2. The student allows the reaction in equation 2.1 to proceed until no more gas is evolved. The volume of O2 in the syringe is now 55 centimeters cubed, measured at room temperature and pressure. Calculate the initial concentration of H2O2. Give your answer to 2 significant figures. Firstly, I've copied over the key pieces of information from part 1 that we're going to use to answer part 2. Then we need to highlight the other bits of information we're given in part 2 that we can then use to answer the question. Firstly, we're told the gas volume of oxygen is 55 centimeters cubed and that it's measured at room temperature and pressure. So we're going to be using the equation volume over molar volume, which in this case, because it's centimeters cubed, will be 24,000 centimeters cubed, equals moles. Then we're told that we need to work out the initial concentration of H2O2, and we need to give our answer to 2 significant figures. We can use this equation to work out the number of moles of oxygen. So that would be 55 divided by 24,000 gives us 2.29 times 10 to the negative 3 moles of oxygen. Then looking at the molar ratio of the equation, we have a 1 to 2 molar ratio. So that means we need to take the number of moles of oxygen, 2.29 times 10 to the negative 3, and multiply them by 2 in order to get the number of moles of hydrogen peroxide. So that would be 4.58 times 10 to the negative 3 moles of H2O2. Then we are working out concentration. So we're going to use the equation triangle N over V times C. So that would be number of moles, 4.58 times 10 to the negative 3 divided by 50 times 10 to the negative 3, because we've taken volume, or 50 centimeters cubed, converted it to decimeters cubed, which gives us a concentration of 0.092 moles per decimeter cubed, which we can then write on the answer line. To get the marks for this question, you get a mark for working out the moles of oxygen, a mark for working out factoring in the molar ratio, so multiplying the moles by 2 to get the moles of hydrogen peroxide, and then you get a mark for working out concentration and giving your answer to 2 significant figures, 0.092. Part B. Hydrogen peroxide can act as an oxidizing agent or as a reducing agent. Some standard electrode potentials are shown below. Use this information to write an equation for a reaction in which hydrogen peroxide can act as a reducing agent. The key words in this question are reducing agent. That means that hydrogen peroxide is going to be oxidized in the overall equation that we create. So that means we're going to use the equation or the electrode potential featuring hydrogen peroxide with the lower electrode potential. And that means that our other electrode potential will need to be reduced, and we're going to use manganese. So the electrode potential with the second highest value, but it's higher than the electrode potential for hydrogen peroxide. And what's going to happen is its oxidation number in manganese will shift from +7 to 2+, and therefore will be reduced, whilst hydrogen peroxide is being oxidized. So what's going to happen, because hydrogen peroxide has a lower electrode potential, its equilibrium is going to shift to the left, whilst the manganese electrode potential is more positive, so it will shift to the right. So rewriting these equations, we would have H2O2 goes to 2H plus O2 plus 2 electrons, and then MnO4 minus plus 8H plus 5 electrons goes to Mn2 plus 4H2O. Next, we need to scale our electrons. We do this by making sure that they're the same number. So we would have to multiply our hydrogen peroxide equation by 5 so that we get 10 electrons, 5 oxygens, 10 H pluses, and 5 hydrogen peroxides. And then we multiply our manganese equation by 2 so that we get 10 electrons and 2 MnO4 minuses, 16 H pluses, 2 Mn2 pluses, and 8 waters or H2Os. So writing the overall equation, we would have 5 H2O2 plus 2 MnO4 minus plus 16 H plus 10 electrons goes to 10 H pluses plus 5 O2s plus 10 electrons plus 2 Mn2 pluses plus 8 H2Os. Next, we can cancel out some aspects of this equation. We can cancel out the electrons first, and then we can cancel out some of the H pluses. We can cancel out all of the 10 on the right hand side, and we can cancel out 10 on the left hand side, so we're left with 6 H pluses. Therefore, making our overall equation 5H2O2 plus 2 MnO4 minus plus 6H plus goes to 5O2 plus 2 Mn2 plus 8 H2O. To get the 2 marks for this question, you get a mark for balancing the 2 equations, so scaling the electrons and making sure that they're both 10, and then you get a mark for the correct overall equation. Part C. Cobalt-2 forms complex ions with water ligands and with chloride ligands. With water ligands, cobalt-2 forms a pink octahedral complex ion, COH2O6 2+. With chloride ligands, cobalt-2 forms a blue tetrahedral complex ion. A student dissolves cobalt-2 sulfate in water in a boiling tube. A pink solution forms. Experiment 1. The student places the boiling tube in a water bath at 100 degrees Celsius. Concentrated hydrochloric acid is added dropwise. The colour of the solution changes from pink to blue. Experiment 2. The student places the boiling tube from experiment 1 in an ice water bath at 0 degrees Celsius. The colour of the solution changes from blue to pink. Part 1. Write the equilibrium equation for the reaction that takes place when the colour of the solution changes. So this question is asking about a ligand substitution reaction. So we're reacting copper 2 with water ligands. So that can be written as COH2O6 2+. And we're told in the question that we're forming a tetrahedral complex. So that means we're going to react with 4 chloride ions because it's a tetrahedral complex with chloride ligands. So 4 chloride ions. And then the equilibrium would produce CO, Cl4, because that's our tetrahedral complex, 2- plus 6H2O. To get the mark for this question, you must have the full complete equilibrium. Part 2. Explain the observations and predict whether the formation of the blue colour is exothermic or endothermic. The first statement we can make is that the equilibrium shifts depending on temperature, but we need to be a little more specific and say that the equilibrium shifts right at 100 degrees Celsius, which we're told in the question because at 100 degrees Celsius, the colour changes from pink to blue, which means it's going from COH2O6 2+ to the blue tetrahedral complex ion, or COCl4 2-. And therefore, that means that the enthalpy change for this equilibrium is endothermic and not exothermic. To get the 2 marks for this question, you get your first mark for stating that the equilibrium shifts right at 100 degrees Celsius. Alternatively, you could say that the equilibrium shifts left at 0 degrees Celsius. And then your second mark comes from saying that it's endothermic. This question is about ethane dioic acid, COOH brackets 2. And ethane dioate ions, COO- brackets 2. Part A. The ethane dioate ion shown below can act as a bidentate ligand. Fe3+ forms a complex ion with 3 ethane dioate ions. The complex ion has 2 optical isomers. Draw the 3D shapes of the optical isomers. In your diagrams, show the structure of the ethane dioate ligands and the overall charge. The key parts of this question is that we're using Fe3+, and that will help when working out our overall charge. Then we need to also factor in the charge of the bidentate ligand, which is minus times 2, so it's 2-. And we are forming 2 optical isomers. So optical isomers, when we draw them 3D, they will be mirror images of each other. So next we need to draw the 3D shapes, so that means using wedges. We will have Fe in the centre, and it will be an octahedral layout of wedges, which is something that you need to know because it comes up quite a lot when talking about transition metals, and so it's really useful to make a revision resource of. Next we need to bond our ligands to our central metal ion, and it will bond with the negative oxygens. So all around our 3D structure or shape, we will bond with oxygen. And then we need to draw the rest of the ligand. So to start, we could have the ligand on the left and then going around the shape to complete it, making sure that when we draw our optical isomer, we have the mirror image. Next, we need to work out the overall charge, so square brackets, and we have Fe3+, and then 3 ligands with a 2- charge. Therefore, the overall charge would be 3-. Next, drawing our second 3D shape, or our optical isomer. Again, we have the same layout, so Fe in the middle, with our octahedral layout of wedges, with 2 dashed at the top and 2 solid wedges at the bottom. Again, it's bonding to the negative oxygens in the bidentate ligand, or the ethane dioate ion. But this time we're going to have the rest of the ligand being the mirror image of the structure we've already drawn. So, as you can see, we can imagine a mirror line, and that is what we're using as our guide to complete the shape of this optical isomer. And then once we've completed the shape, we need to add its overall charge, which would be the same. It would be 3 minus. To get the 3 marks for this question, you get a mark for each correct optical isomer in their 3D shape, and then you get a mark for the correct overall charge, so 3 minus. Part B. Ethane dioic acid COOH brackets 2 is present in rhubarb leaves. A student carries out a redox titration using aqueous cerium 4 sulfate, Ce brackets SO4 brackets 2 aqueous, to determine the percentage by mass of ethane dioic acid in rhubarb leaves. In the titration, Ce4 plus aqueous ions oxidize ethane dioic acid in hot acid conditions. Ce4 plus aqueous ions have a yellow color. Ce3 plus aqueous ions are colorless. The student weighs 82.68 grams of rhubarb leaves and extracts ethane dioic acid from the leaves. The ethane dioic acid is added to dilute sulfuric acid to form a colorless solution, which is made up to 250 centimeters cubed with distilled water. The student heats 25 centimeters cubed of this solution to 70 degrees Celsius and titrates this volume with 0.05 moles per decimeter cubed CeSO4 from the burette. The student repeats the titration to obtain concordant brackets consistent titers. Part 1. This titration is self-indicating and the student does not need to add an indicator. What color change should the student observe at the end point? Firstly, for this question, we need to look at where we're told a color. So we're told that Ce4 plus ions are yellow in color, and that Ce3 plus ions are colourless. We're also told that ethane dioic acid is added to dilute sulfuric acid and forms a colourless solution, and that this colourless solution is titrated with CeSO4 So that would be Ce4 plus, because sulfuric acid, or the ion in sulfuric acid, SO4, has a 2 minus charge, and there are 2 ions, so therefore it must be Ce4 plus to have an overall charge of 0. So that would mean that our colour change for this titration is from colourless to yellow. Now, where a lot of people fell short on this question is they looked at the ions and the Ce4 plus ion going to the Ce3 plus ion, so yellow to colourless, but that's not what we're looking at. We're looking at the titration itself, and what we're doing is we're titrating a colourless solution with a yellow coloured ion, so colourless to yellow. To get the mark for part 1, you need to say colourless to yellow. Part 2, calculate the percentage by mass of ethane dioic acid in the rhubarb leaves. Give your answer to an appropriate number of significant figures. Firstly, with this question, we need to work out the titers of the titration results. So that would be taking the final reading and subtracting the initial reading. So for titration 1, that would give us 23.25. For titration 2, that would give us 23.50. Notice I'm giving all of my answers to 2 decimal places because that is what you would do when recording volume in a burette. And then for titration 3, we're left with 23.15. So next we need to work out the mean titer. So the mean titer would be using the concordant results. The concordant results are within plus minus 0.10 centimeters cubed of each other. So that would be titration 1 and titration 3. That would give us a mean titer of 23.25 plus 23.15 divided by 2, which equals 23.20 centimeters cubed. Using the mean titer, or the volume, and the concentration of CeSO42 or Ce4+, we can then use the equation triangle of NV times C to work out the number of moles of Ce4+. So that would be 23.20 times 10 to the negative 3, because we're converting centimeters cubed into decimeters cubed, and then multiplied by concentration, which is 0.05, and that would give us a number of moles of 1.16 times 10 to the negative 3 moles. These are the moles of Ce4+, and we're trying to work out the moles of ethane acid, so we need to look at the equation of Ce4+ to ethane acid. That's a 2:1 molar ratio. So to work out the moles of ethane acid, we take 1.16 times 10 to the negative 3 and divide by 2, which gives us 5.80 times 10 to the negative 4 moles of ethane acid in 25 centimeters cubed. But we want the number of moles in 250 centimeters cubed. And it's because we're taking a 25 centimeter cubed sample, but overall we have 250 centimeters cubed. So we have a factor of 10 we need to account for. So that means we need to do 5.80 times 10 to the negative 4 multiplied by 10, which gives us 5.80 times 10 to the negative 3 moles of ethane acid, COOH, brackets 2, in 250 centimeters cubed. We're asked to work out the percentage by mass, and we're going to do this using an equation triangle of mass over moles times relative formula mass. So we have moles and we want to work out mass, so we need the relative formula mass of ethane acid, and we're going to multiply our number of moles by this number. So that would be 5.80 times 10 to the negative 3 multiplied by 12 plus 16 times 2 plus 1 times 2, all in brackets. So 12 comes from carbon, 16 times 2 is the 2 oxygens, and plus 1 is the hydrogen, all multiplied by 2 is the relative formula mass of ethane acid. And that would give us 0.522 grams. Finally, working out the percentage by mass, we need to do 0.522 divided by the mass we're told in the question, 82.68 grams. So that's what we're going to divide by, 82.68, and then we're asked for a percentage, so multiply by 100. That gives us 0.631% to 3 significant figures, because we're told in the question to give our answer to an appropriate number of significant figures, in this case 3, making our answer on the answer line 0.631. To get the 6 marks for this question, you get a mark for correctly working out the mean titer, or 23.20 centimeters cubed, a mark for working out the moles of Ce4+ correctly, 1.16 times 10 to the negative 3. You get a mark for working out the number of moles of ethane acid in 25 centimeters cubed, which is 5.8 times 10 to the negative 4 moles. And then you get a mark for working out the moles in 250 centimeters cubed, or 5.80 times 10 to the negative 3 moles. You then get a mark for working out the mass of ethane acid and the percentage by mass of ethane acid, so 0.631, and giving your answer to 3 significant figures. That gets you your final 6th mark. This question is about 2 compounds used in medicine. A. Cisplatin, PtCl2, brackets NH3 brackets 2, is a complex of platinum which is used in cancer treatment. Part 1. What is the oxidation number of platinum in cisplatin? In cisplatin, we have platinum, and we're trying to work out the oxidation number of platinum. We have chlorine, but we have 2 chlorines, and we have ammonia, or NH3, and we have 2 ammonias. Then if we work out the oxidation numbers, in chlorine has a -1 oxidation number, and there are 2 in cisplatin. So we need to multiply this by 2, and we get -2 for the oxidation number of chlorine in cisplatin. Ammonia is a neutral compound and therefore would have an overall oxidation state of 0. And there are 2, so we multiply 0 by 2 and we get 0. In any compound, we need to have an overall oxidation number of 0. So far we have -2 and 0, which means that the oxidation number of platinum must be +2, which is what we write on our answer line. To get the mark for this question, you need to write +2 in the answer line. Part 2. Cisplatin is prepared in a ligand substitution reaction which takes place in multiple steps. The equation for the final step forming cisplatin is shown below. In the box, outline the mechanism for the formation of cisplatin from PtCl3 NH3-. Use curly arrows and lone pairs where appropriate. We're going to begin answering this question by drawing the 3D structure of the complex we've been given in the question. When you're given a 3D structure as a product or reactant, it's really important when finishing the mechanism that you draw it in the same way. So we've got dotted wedges at the top and solid wedges at the bottom of the complex. So then we would have 3 chlorines across the complex and an NH3 or ammonia, making sure that the nitrogen of the ammonia bonds to the platinum. We finish by drawing square brackets around our complex. Now our complex is going to react with NH3 or ammonia, and there's going to be a lone pair on the nitrogen. The centre of this lone pair, we are going to draw a curly arrow to the platinum and a curly arrow from the platinum-chlorine bond to the chlorine. We do this because that means we're going to form the platinum-ammonia bond, as shown in our product, and the Cl-, which is our second product. To get the 2 marks for this question, you get a mark for your curly arrow from the lone pair on the NH3 or ammonia to the platinum, and your second mark for the curly arrow from any platinum-chlorine bond in the complex. I've chosen to do the bottom left because that is where our next ammonia or NH3 is going to be added to the complex, so therefore it's easier to check when looking back at your answers. Part B. Paracetamol is a solid organic compound used in tablets as a painkiller. Part 1. Name the functional groups present in paracetamol. For any question where you're asked to name functional groups, using colours is really important and helpful to identify the different functional groups. If we identify our first functional group on paracetamol, we have a phenol group. A way to identify a phenol group is a benzene ring with an alcohol group attached. Then, using a different colour, we can identify our second functional group, and that is the NH here bonded to our carbonyl. A carbonyl group is a C double bonded to an oxygen. And this functional group is known as an amide functional group. To get the 2 marks for this question, you get your first mark for saying phenol and your second mark for saying amide. Part 2. A chemist prepares a pure solid sample of paracetamol from 4-nitrophenol in 2 stages. Describe a 2-stage synthesis of 5.00 grams of pure paracetamol from 4-nitrophenol. The overall percentage yield of paracetamol from 4-nitrophenol is 40.0%. In your answer, include the mass of 4-nitrophenol required, the reagents and intermediate, and details of the purification of paracetamol. To begin, we're going to work out the mass of 4-nitrophenol required. In order to do this, we need to work out the moles of paracetamol. We work out moles using an equation triangle, which I'll draw now. The equation triangle has mass at the top, and if it's at the top, it means it's going to be divided by whatever's on the bottom. On the bottom, we have moles times relative formula mass. So what this equation triangle means is that moles times relative formula mass equals mass, or mass divided by moles equals relative formula mass, and so on. So if we're working out the moles of paracetamol, we need the mass and the relative formula mass. We're given the mass in the question, 5 grams. So we would have 5 divided by the relative formula mass. Next, we're going to work out the relative formula mass by counting the number of carbons first. So in paracetamol, we have 1, 2, 3, 4, 5, 6, 7, 8 carbons. So we would have 12 times 8. Then we're going to count the number of oxygens. We have 2 oxygens, so we'll have 16 times 2, plus the number of nitrogens. This is 1 nitrogen, so we would have 14. And then we're going to work out the number of hydrogens. Hydrogens are always the trickiest part when working out the relative formula mass because they're easier to forget. But if we start on the benzene ring of paracetamol, we have 1, 2, 3, 4, 5 with the 1 in the OH, 6, and then plus 3, which is 9. And that means that our relative formula mass is 151. So 5 divided by 151 is equal to 0.0331 moles. Next, we need to work out the moles of 4-nitrophenol, and that would be taking the moles 0.0331 and multiplying them by 100 over 40. I'm doing this because we're told in the question that we have a 40% percentage yield. That gives us the number of moles of 4-nitrophenol as 0.0828 moles. But we want the mass, so using our equation triangle, we need the moles times the relative formula mass. So that would be 0.0828 multiplied by the relative formula mass, which I'll now work out. So again, counting the number of carbons. We have 1, 2, 3, 4, 5, 6 carbons. So we would have 12 times 6. Plus the number of oxygens. We have 3 oxygens. So we have 16 times 3. Plus the number of nitrogens. Well, that's 1 nitrogen again, so that's plus 14. And then the number of hydrogens. On the benzene ring, we have 1, 2, 3, 4, 5 if we count the 1 in the OH group of the benzene ring. So that's 5 in total, so we need to add 5. And that gives us the relative formula mass of 4-nitrophenol as 139. And that would give us the mass of 4-nitrophenol required as 11.50 grams. Notice I've written the mass to 2 decimal places. Next, we're going to work out the reagents and intermediate. The name of the intermediate is 4-aminophenol. And if we were to draw this, we would still have our phenol group, which is our benzene ring, with our OH group attached. But instead of NO2, we have NH2. In order to create 4-aminophenol, we need reducing reagents, and they would be tin or SN and concentrated hydrochloric acid, which is what we write next to our intermediate. The reason the intermediate is what it is, and why we've replaced the nitro group, so the NO2, with an amine group, or NH2, is because when the NH2 reacts with an acyl chloride, the chlorine comes off along with 1 hydrogen in the amine, and that forms HCl, or hydrochloric acid. and then you form an amide bond, which is our NH with a C doubly bonded to a oxygen or an O. And that's what we formed in paracetamol. So that's why the intermediate is what it is. Now we're going to talk about the details of the purification of paracetamol. We're going to write the steps of purification as bullet points because they're easier to check later on. Our first bullet point we need to write for this question is that we're going to dissolve an impure solid in a minimal amount of hot solvent. This is a phrase that comes up quite often when talking about purification in organic chemistry. Then we're going to write our second bullet point, and our second bullet point is that we need to cool the solution and filter the solid. Cooling and filtering are always really important when talking about purification. Again, these are steps that come up quite often. Our third bullet point is that we're going to scratch with a glass rod. This is a step that doesn't often come up in purification, but is really important in this specific type of purification when you're looking for a pure solid. And finally, we're going to wash with a cold solvent and dry. Washing and drying with cold solvent is often the final step of purification. To get the 6 marks for this question, you have to have the correct calculation of the mass of 4-nitrophenol, correctly identify the reagents and intermediate, and have a detailed description of most of the purification steps. A student carries out 2 experiments in the laboratory based on succinic acid, butane dioic acid, CH2COOH brackets 2. Part A. Aqueous succinic acid can be neutralized by aqueous sodium hydroxide, NaOH. This reaction can be used to determine a value for the enthalpy change of neutralization. The student follows this method. Add 50.0 centimeters cubed of 0.400 moles per decimeter cubed succinic acid to a polystyrene cup. Measure out 50.0 centimeters cubed of 1.00 moles per decimeter cubed of NaOH, which is in excess. Measure the temperature of both solutions. Add the NaOH to the aqueous succinic acid in the polystyrene cup. Stir the mixture and record the maximum temperature. Calculate a value for the enthalpy change of neutralization in kilojoules per mole. Assume that the density of all solutions and the specific heat capacity C of the reaction mixture are the same as for water. Firstly, we need to highlight the key pieces of information in this question. Our first key piece is that we've got 2 moles of H2O, or a 2 molar fraction. And that's important because the enthalpy change of neutralization is the energy released when forming 1 mole of H2O, and we've got 2, so that means our final answer will have to divide by 2. Our next key piece of information is our volume and concentration of succinic acid. We're going to use these to work out the moles of succinic acid. Then we need to look at our temperature readings because we will be using temperature change. So as I've said, our first action that we're going to do is we're going to work out the moles of succinic acid. We do this using an equation triangle of NV times C, which means we're going to take volume and multiply this by concentration to get the number of moles of succinic acid. So that would be 50 times 10 to the negative 3 because we're converting centimeters cubed into decimeters cubed, and then multiply by 0.4, which gives us 0.02 moles of succinic acid. Next, we're going to use Q equals mc delta T. If we label this equation with the information we already know, well, m is mass, and that will be the total volume because we're told that the density of all solutions is the same as water. So 1 centimeters cubed equals 1 gram. And the total volume is 100 centimeters cubed, so our total mass would be 100 grams. C is specific heat capacity. Again, we're told it's the same as for water. So in our data sheets, we're told that it's 4.18. Delta T is the temperature change which we can calculate, would be 26.5 minus 21.5, which gives us 5 degrees Celsius. This means that Q would be Q equals 100 times 4.18 times 5, which then equals, in joules, 2090 joules. But we want kilojoules per mole, so converting this to kilojoules, we would get 2.090 kilojoules. Then we can work out kilojoules per mole, because we've already calculated moles, and this would be 2.090 divided by 0.02, which gives us plus minus 104.5 kilojoules per mole. But the very first thing I said was that we need to divide our answer by 2 because we have 2 water molecules produced. So it would be 104.5 divided by 2, which equals 52.3. And we need a negative sign in front of our 52.3 because the enthalpy change of neutralization is negative. To get the 4 marks for this question, you get your first mark for working out the number of moles of succinic acid, 0.02. Your second mark for working out Q, or 2090 joules. Your third mark for working out 104.5 and that this is positive or negative at this stage. And then your fourth mark for working out that you need to divide this by 2 because there are 2 water molecules produced, and writing minus 52.3 on the answer line. Part B. Succinic acid is esterified by ethanol, C2H5OH, in the presence of an acid catalyst to form an equilibrium mixture. The equilibrium constant Kc for this equilibrium can be calculated using the amounts in moles of the components in the equilibrium mixture, using expression 5.1. A student carries out an experiment to determine the value of Kc for this equilibrium. The student mixes together 0.0500 moles of succinic acid and 0.150 moles of ethanol with a small amount of an acid catalyst. The mixture is allowed to reach equilibrium. The student determines that 0.0200 moles of succinic acid are present in the equilibrium mixture. Part 1. Which technique could be used to determine the equilibrium amount of succinic acid? So the answer to B part 1 is titration, and writing titration on the answer line would get us our mark for this part of the question. Part 2 says that we need to write the equation for the equilibrium reaction that takes place. For this part of the question, we need to look at our expression for Kc, and Kc is written as products over reactants, and the power that it's raised to shows us the stoichiometry of the equation. So, using this information, we can work out the equilibrium reaction that takes place and write this. So, our reactants would be brackets CH2COOH brackets 2 plus 2, because it's raised to the power of 2, C2H5OH, and then we need an equilibrium arrow, and then we would produce brackets CH2COOC2H5 brackets 2 and 2H2O. To get the mark for this question, you need to have the full complete equilibrium reaction. Part 3. Draw the skeletal formula of the ester present in the equilibrium mixture. The ester they're asking us to draw is here, which I've just highlighted. If we start by drawing our first ester link, because this is a repeating ester, we would have our oxygen bonded to a carbon, which is then doubly bonded to an oxygen. Our first ester link will be connected to our C2H5, which would be 2 peaks of skeletal formula. Then we mirror what we've drawn on the left with our C doubly bonded to an oxygen and then bonded to another oxygen. But this ester has a side chain, it has our CH2, so we need to account for this in our skeletal formula. So at the ends, we need to draw another peak showing another carbon in this ester. To get the mark for this question, you need to have the full, complete, correct ester drawn. Part 4. Kc is the equilibrium constant in terms of equilibrium concentrations. Why can expression 5.1 be used to calculate Kc for this equilibrium? The reason why expression 5.1 can be used is that the volumes cancel. Alternatively, you could say that there are the same number of moles of products and reactants, or the same number of moles on both sides of the equation, so they're going to cancel as well. To get the mark for this question, you need to either say that the volumes cancel, or that there are the same number of moles on each side of the equation, or the same number of moles of products and reactants. The reason why this is the answer for question 4, or the reason why there are the same number of moles of products and reactants, we can tell this from the Kc expression, or expression 5.1. And so we can see that we've got on the numerator something raised to the power of 1 and something raised to the power of 2. And on the denominator, we've got something raised to the power of 1 and something raised to the power of 2. So that means that the stoichiometry of the equation, we're going to have a 1, 2 on the reactants and a 1, 2 on the products as well. And so that means that there's going to be the same number of moles of products and reactants based on the stoichiometry. Part 5. Calculate the value of Kc for this reaction. Show your working. In this question, we're going to firstly highlight the key pieces of information, and that would be any reference to moles, because we're going to use the number of moles left in the equilibrium mixture to work out the value of Kc. And that's because we're going to use a method called ICE in this video. So firstly, using this method, we need to write our reactants, CH2COOH brackets 2, C2H5OH, and our products. So that would be CH2COO C2H5 brackets 2 and H2O. We then use the information in the question. I stands for initial number of moles, and our products initially would have 0, so we can fill this in the table. We're told that initially we have 0.05 moles of succinic acid and 0.15 moles of ethanol in our mixture. We then need to work out the change. We do this using the equilibrium value of moles of succinic acid that we're given, and we're told that it's 0.02. So that means we have a change of negative 0.03, and we can apply this change to anything with the same stoichiometry. So for our products, we would have the opposite change but the same value. So it'd be plus 0.03, making the number of moles present at equilibrium 0.03 for our ester. For water and ethanol, or H2O, and C2H5OH, we have double the number of moles. So our change would be doubly as big. So that'd be 0.06 or minus 0.06 for ethanol and plus 0.06 for water. So we know the water moles at equilibrium, and the ethanol moles at equilibrium would be 0.15 minus 0.06, which gives us 0.09 moles of ethanol in the equilibrium mixture. So now we're going to plug in the numbers that we've just calculated for the number of moles in the equilibrium mixture. We're going to use our expression for Kc and plug in the moles. So that would be 0.03 times 0.06 to the power of 2. We're applying the same powers of 2 as we're given in the expression for Kc, and we would divide by 0.02 times by 0.09 to the power of 2. That gives us a value for Kc of 0.67, which we will then write on the answer line for this question. To get the marks for this question, you get your first mark for correctly calculating the number of moles in the equilibrium mixture for your products, so the ester and water. You get your second mark for working out the number of moles in equilibrium for ethanol, or 0.09 moles, and your third mark for correctly substituting the number of moles you've calculated in the equilibrium mixture into your expression for Kc, and finding that it's 0.67. This question is about organic reactions. Part A. Compound A is formed when ethanol is mixed with OH- aqueous ions, which act as a catalyst. The balanced equation is shown in reaction 6.1 below. Part 1. Give the systematic name for compound A. The first thing we need to do when giving something a name is number the longest carbon chain in the compound. So working from the functional group, we would go 1, 2, 3, 4. There are 4 carbons in the longest carbon chain of compound A, so that means we're going to use the prefix but. Next, we need to identify key groups in compound A. We have an OH group and an aldehyde group. So in the name, we're going to have hydroxy to signify the OH group. But we're going to have a 3 because it's on carbon number 3. So we'd have 3-hydroxy but to signify the 4 carbons. And then the aldehyde group we show by saying but-an-al, which is the suffix for an aldehyde group. To get the mark for this question, you need to have the full correct systematic name for compound A. Part 2. What type of reaction has taken place? The type of reaction we've seen in reaction 6.1 is known as an addition reaction because there is no other product produced. So both reactants form the singular product, compound A, or 3-hydroxybutanol. To get the mark for this question, you need to write addition on the answer line. Part 3. Reaction 6.1 takes place in 2 steps. OH- ions act as a catalyst. In step 1, ethanol reacts with OH- ions to set up an acid-base equilibrium. In step 2, compound A is formed. Complete the equilibrium for step 1 and label the conjugate acid-base pairs as A1, B1 and A2, B2. Suggest the equation for step 2. Firstly, let's identify the acid and the base out of CH3CHO and OH-. The acid is CH3CHO, so we can label this A1 using the correct labels that we've been given in the question. Our base is then OH-, so we'll label this B2. The acid, CH3CHO, is a proton donor, so it's going to donate a hydrogen to OH-, which means we're going to produce H2O and CH3CO-. Finishing the labels, we would have A2 and B1. If we just look back and check for a second, the acid and base conjugate pairs and why they are what they are. So looking at A1 and B1, so A1 means acid number 1, and acid is a proton donor, and we can see that A1 going to B1, well, it's lost a hydrogen or an H+, which is also known as a proton. Then B2 and A2, a base is a proton acceptor, and going from B2 to A2, we've gained an H+, or a proton, and so it has accepted a proton and is the base. And so we can check that we've got the correct conjugate acid-base pairs by using the fact that an acid is a proton donor and a base is a proton acceptor. Now we need to suggest an equation for step 2. So we're told that step 2 is where compound A is formed. So if we refer back to part A, we can see the balanced equation 6.1, which shows compound A being produced. If we label the reactants in this reaction, we have CH2CHO minus CH3CHO and compound A, which would produce OH- ions as well, so we need to add H2O as one of our reactants. If we copy this for part 3 in our answer line, so that would be CH3CHO plus CH2CHO minus plus H2O forms compound A, which we can write as CH3, CHOH, CH2, CHO, and OH minus ions. To get the 3 marks for this question, you get a mark for having the correct equilibrium equation, a mark for the correct labels, and a mark for the correct equation for step 2. Part 4. A similar reaction takes place when propanone, CH3(2CO), is mixed with OH minus aqueous ions. Draw the structure of the organic product of this reaction. So, like reaction 6.1, we're going to form a hydroxy group. So we would have CH3 bonded to a COH and a CH3, and then this is connected to a ketone group, and the ketone group would be CH2 bonded to a carbon with a doubly bonded oxygen and a CH3 group attached as well. To get the mark for this question, you must have the correct structure for the organic product of this reaction. Part B. Many organic reactions use electrophiles as reagents. Explain the role of electrophiles in organic chemistry. Your answer should include one reaction of an aliphatic compound and one reaction of an aromatic compound, including relevant mechanisms. There are 2 mechanisms you'll learn about at A level that involve electrophiles. The first is electrophilic addition, and it's between an alkene and a halogen or a hydrogen halide. We're going to use ethene and bromine here. So here I'm drawing ethene, and I'm going to draw bromine, one with a positive dipole and one with a negative dipole. There will be a curly arrow from the centre of the bromine bond to the negative dipole and from the centre of the carbon-carbon double bond to the positive dipole, because the electron-dense region is attracted to the electrophile. We then attach the bromine, and our intermediate will have a positive charge where the consequent bromine, the negative charge, is yet to join. So there will be a curly arrow from the lone pair on this negative bromine to the positive intermediate carbon. And we will form a haloalkane as our product. Then we're going to talk about electrophilic substitution, which is our second mechanism you learn about at A level. But for this mechanism, you need to form your electrophile. So to form our electrophile, we need to react H2SO4 with HNO3 in this case, because we're doing a nitration of benzene reaction. So we'll form NO2 plus, H2O, and HSO4 minus. The benzene ring, the ring in the benzene, is an electron-dense region, and so will be attracted to our electrophile, which is NO2 plus. And then we'll form our intermediate, again a positive intermediate, where we have a half completed benzene ring with a positive charge, a hydrogen, and an NO2 group ready to be attached at the end. The hydrogen is reattracted to the benzene ring, and we form then a benzene ring with an NO2 group and an H+. This is nitration of benzene, but we need to reform our catalyst. Our H+ is then reacted with our HSO4 minus and forms H2SO4. To finish this question, we're going to define an electrophile. Electrophiles act as electron pair acceptors. This is a definition for an electrophile. It might be a 1-mark question later on in an exam. To get the 6 marks for this question, what we need to do is describe in detail the electrophilic reactions and mechanisms of one aliphatic and one aromatic compound. In this question, we haven't written a long detailed explanation. We've labelled our mechanisms and drawn diagrams of the mechanisms for an aliphatic and an aromatic compound, so it's the same as writing a long explanation.